Last time, we looked at a static imprint of a single thought. But subjective experience isn't a still frame, it is an emergent property. It arises instantly out of a complex, dynamical web of interactions. To understand this, you have to look at the brain's degrees of freedom. Imagine that every tiny variable in the brain, like the level of activity in a small patch of cortex, or how strongly two regions are talking to each other, is a separate value that can change. All of these changes, spread across space and time, form a messy spatiotemporal pattern. Each of those variables is a dimension. At any single instant, the specific combination of all those values creates the state of your mind right now. Mathematically, that creates a state space with tens of thousands of dimensions. We can't visualize that kind of complexity. So, the algorithm I'm using here takes all those thousands of independent variables and calculates the three main components that matter most. It distills that massive web of activity into a single coordinate in 3D space. The specific method I'm using is called T-Fate, from a recent paper that builds low-dimensional trajectories of brain activity during continuous movies. Here, I'm taking real fMRI data from a person watching a short animated film and running it through the same T-Fate model as in the original paper. The algorithm turns each moment of their brain activity into a single point in this 3D space. When you line those points up over time, you get a trajectory. The authors of the T-Fate paper found that these low-dimensional trajectories don't just mirror the raw sensory input. They line up with meaningful changes in the movie that people consistently mark as new events. It seems to represent a unified, subjective state. To make sense of the story, the brain is binding together vision, logic, expectation, and emotion into one singular configuration. When the plot creates a feeling of tension, relief, or a sudden realization, the brain's internal pattern shifts and the path turns into a new direction. So this line you see is a geometric compression of how that unified subjective experience changed over time. Not the full richness of what it felt like, but a compact spatial trace of how the experience evolved from moment to moment.
But we can ask a deeper question. If we did this for many people, many moments, many mental states, would all of those trajectories live inside some common, low-dimensional shape? Would being awake and conscious occupy one characteristic region of this space, while deep sleep or dreaming carves out a completely different geometry? Is there, in some sense, a geometry of the human soul hiding in these data? To get closer to that, I turn to a different method called two-step diffusion maps, or 2SDM. Unlike the previous algorithm, this one is designed to find common structure across many brains. In a recent paper, the authors took fMRI from many people doing tasks like working memory, simple motor actions, social and emotional judgments, gambling, and so on, and embedded all of those time points together into a single low-dimensional manifold. In that space, the points form a structured wing-like shape in 3D. Different tasks occupy distinct regions, corresponding to a small set of recurring brain states that show up across tasks. When they embed resting state data from the same individuals, those time points also land on the same manifold and fall into the same clusters, suggesting that rest is made up of the same basic states that appear during tasks. Nearby points correspond to similar global brain dynamics. Moving across the manifold is like sliding through nearby states of mind. If the T-Fate trajectory shows how a single experience traces out one path through state space, this 2SDM manifold is more like the landscape that many such paths live in, a shared low-dimensional terrain of brain states. In my own project, I used essentially the same 2SDM pipeline on resting state fMRI only. I focus purely on awake rest, and the scans have slightly lower spatial resolution, so the shape isn't identical, but the overall structure is very similar. To me, it is beautiful.
It looks like a butterfly or a bird with two broad, curved wings in 3D, and it reminds me a little of the famous Lorenz attractor. These wide, sweeping wings feel like the huge range of states a waking human mind can explore, a rough map of everywhere a conscious mind can go. I also checked this with two independent resting state datasets. Each time, the same kind of butterfly-like structure appeared, very similar to the awake manifold reported in the original 2SDM work. Then I asked, what happens when we're not awake? So I took sleep fMRI data and processed it through the same 2SDM pipeline. This time, the manifold had a completely different overall form, less like a butterfly, more like a funnel or a thick tree trunk with branching roots. In my data, and in contrast to the awake results, it really does look as if this butterfly-like structure is a characteristic shape of the awake, responsive brain, while sleep lives in a different part of the landscape, with a different geometry. If anything here deserves to be called a shape of the soul, this awake butterfly is probably the closest thing we have right now. This manifold is not a path through time, it's more like an energy landscape of the awake brain. Each point is one possible configuration. The cloud as a whole is the terrain of states we tend to visit. Every dot still comes from a real moment in a real scan. In the original 2SDM paper, the authors clustered this terrain into four recurring brain states: fixation, transition, lower-level cognition, and higher-level cognition. In the original work, they summarized the dynamics between these four states with a Markov chain. Basically, how often you hop from one state to another and how long you tend to dwell in each. I also tried to color the manifold using the actual entropy of the brain activity at each point. Very tentatively, this also seems to split the space into clear clusters. So there seems to be a connection between where you are on the manifold and the entropy of the underlying brain state. This needs proper validation, so treat it as a hypothesis, not a confirmed result. But it's interesting, given how many modern theories of consciousness tie awareness to the entropy or diversity of brain dynamics. Every dot still comes from a real moment in a real scan. If you connect them in temporal order for each person, we see the state of mind walking across this manifold, tracing out a path through the terrain over time. I turned each time point into a particle following its own trajectory on the butterfly. When you look at those paths, we can already see some patterns. Transitions directly from the tip of one wing to the tip of the other are rare, and most of the motion travels along the wings, with particles moving in both directions. If you filter out the points by how fast they move along their paths, the slowest ones tend to cluster in the central region between the wings, while the fastest ones live out in the wings. To push the analysis even further beyond the original work, I use a technique called a mixture density network, or MDN. In simple terms, it's a neural network that learns a smooth vector field from these tangled paths. For each location, it estimates the main directions in which states tend to move. It turns the cloud of points into a map of flow tendencies. An MDN doesn't just give a single flow, it represents the field as a mixture of several components, one dominant, strongest flow pattern and additional, weaker subflows. The dominant flow component is fairly simple. States tend to drift from the outer wings toward a central basin lower in the manifold, as if the dynamics keep being pulled back toward a preferred, baseline region of state space. That fits with the idea that even when the mind wanders, its activity fluctuates around some stable background configuration. More interesting is the second, weaker flow component. On the shorter wing, the flow splits into two twisting streams that wrap around each other and loop back on themselves, forming a more complex looping pattern rather than a single, straight drift. When I compare this to how the trajectories are colored by that entropy-like measure, and here I mean the entropy of the paths themselves, not of the raw brain signal, that same region stands out as one where paths change direction more often and the local dynamics look more intricate. Because this comes from a weaker MDN component, some of that structure could still be noise, so it's something to keep in mind rather than a solid claim. We can take one more conceptual step, and this part is quite speculative. You can imagine dropping a little probe onto the manifold and letting it follow one of these MDN flow lines, and then asking, as we move along this path, which brain regions start to contribute more to the overall state, and which contribute less. It doesn't show literal information flowing along tracks. Each arrow is really showing how the influence of different regions on the low-dimensional state changes as you move across the manifold. A region can light up in this view because it suddenly matters more for shaping the state space at that point, not necessarily because its raw activity just spiked. On the longer wing, going from tip to root is a clear many-to-few collapse. Near the tip, a large set of regions across the back and sides of the brain all contribute at once, and that's where the fMRI entropy peaks. As you move down toward the root, that pattern tightens. Fewer, more specific frontal and occipital areas, plus a couple of focused temporal sites, carry more of the load, and you end up in a lower entropy cluster near the base of the wing. Paths that pass closer to one edge may emphasize slightly different sets of regions, but in all cases it looks like many contributing areas being reduced to a smaller, more stable set. On the shorter wing, the geometry is almost reversed. The tip starts out with only a few deep and occipital contributors, and as you flow down toward the root, more and more of the cortex is pulled in, especially frontal and parietal regions. The manifold here goes from few to many. For example, a compact change or conflict signal may be amplified into a more widespread pattern that could support an update of what you're about to do or pay attention to. The MDN even hints at several partially distinct lanes along this surface. Very tentatively, one might be more linked to externally driven changes and another more to internally timed ones. But that subdivision is definitely the weakest and most speculative part of the picture. The last trajectory goes all the way from the tip of one wing to the tip of the other. When states leave the longer wing and head toward the shorter wing, a broad set of posterior and midline regions gradually converges onto a single deep point in the nucleus accumbens. In the reverse direction, that same small region sends influence back out into a wider posterior pattern. So, for now, all we can really say is that this one deep hub sits on many of the paths that jump between wings, making it an interesting place to look if we want to understand how the brain moves from one patch of this manifold to another. But at this point, we're already deep into the analysis and well beyond the original research paper's methods. So all these patterns would need careful, rigorous research to validate, so please don't treat them as established facts. In the end, all of this collapses into this single manifold, a form that wasn't designed, but condensed out of information itself, like a sculpture carved by nature. And maybe what you're seeing here is one of the first clear contours of that other world.